Hey everyone, today we are going on a pretty incredible journey. We're going to try and map reality itself. Not a country, not a planet, but, well, everything. And to do that, we have to start with the biggest, most fundamental question there is.
I mean, what is it really made of? Go past the chair you're sitting on, past the molecules, past the atoms. What are the ultimate, indivisible little bits that make up you, me, and everything else in the entire cosmos? It's one of the biggest questions we've ever dared to ask.
And for the last 50 years or so, our best answer to that question has a name: the Standard Model of Particle Physics. Now, don't think of it as some scary, complicated theory. It's much better to think of it as a map. It's the most detailed, most successful map we've ever made of the fundamental bits and pieces that make up our universe.
Okay, so every good map needs landmarks, right? Well, the first set of landmarks on our map are the particles that actually make up stuff. You know, the tangible building blocks of reality.
Physicists call these particles fermions. But a much better way to think about them is as the universe's ultimate Lego bricks. Seriously, as far as we know, you can't break them down any further. They are the absolute base level of all physical matter. And these Lego bricks, they come in two main flavors: quarks and leptons. You can think of quarks as the really social ones. They love to hang out in groups to form protons and neutrons deep inside the heart of an atom. Leptons, on the other hand, are kind of the loners. The most famous one, of course, is the electron, which is that little particle buzzing around the outside of the atom.
So let's zoom in on those quarks for a second. There are 6 types, or flavors, and yeah, they have some pretty fun names like charm and strange. But here's the mind-blowing part. All the normal matter that you and I ever interact with, everything, is made from just the first 2, the up and the down quarks. That's it. A proton is just 2 ups and a down. A neutron is 2 downs and an up. The entire world is just endless combinations of those 2 things.
And here's the other side of the family, the leptons. You've got the electron, which we all know and love. Then you have its 2 heavier, sort of unstable cousins, the muon and the tau. And then there are these 3 incredibly weird, shy particles called neutrinos. Trillions of them are passing through your body right now without you feeling a thing. And that's it. Those are our 12 Lego bricks.
Okay, so we have our building blocks. But a pile of Legos doesn't just build itself into a castle, right? You need rules. You need forces. You need some kind of cosmic glue that tells all these bricks how to stick together.
Well, that cosmic glue comes in the form of another class of particles called bosons, and they're really cool. If the fermions are the bricks, then the bosons are like little messengers constantly flying between them, carrying messages that say pull together or push apart. They are the carriers of the fundamental forces of nature.
And there are 4 of these fundamental forces. You've got the strong force, which is like this ridiculously powerful superglue holding the centers of atoms together. There's the electromagnetic force, which is behind everything from electricity to sunlight. Then the weak force, which is involved in radioactive decay. And then there's gravity, the weird one. The one that, as we're about to see, doesn't quite fit in with the others.
We've seen the matter particles, the bricks. We've seen the force particles, the messengers. Let's put it all together and look at the complete map. This is it, our entire inventory of the universe's fundamental particles. Let's break it down real quick.
First up, we've got our 12 matter particles, the fermions. Those are our 12 Lego bricks. 6 quarks, 6 leptons. They make up all the substance, all the stuff in the universe.
And next we have the force carriers. The gluon handles the strong force. The photon takes care of electromagnetism. The W and Z bosons manage the weak force. But wait a second, there's one more particle on that list, a really special one that was the final missing piece of this whole puzzle for a very long time.
And that is the Higgs boson. Finding this particle back in 2012 was a huge deal. Here's why.
The Higgs is connected to a hidden energy field that fills the entire universe. As other particles move through this field, they interact with it, and that interaction is what gives them their mass. Without the Higgs, everything would be massless and just zip around at the speed of light. The universe as we know it couldn't exist.
So there it is, our whole map. 17 fundamental particles. And the power of this model is just staggering. These particles and the rules they follow can successfully predict the outcome of basically every single particle experiment we've ever done. It is, without a doubt, one of the most successful theories in the entire history of science.
But just like those old maps of the world that had dragons and sea monsters drawn at the edges, our map has some pretty big unexplored territories. There are parts of the map that are just blank. Which, of course, brings us to the biggest question for any physicist alive today. After all this incredible success, are we done? Is the map finished? Is this the final story of how reality works?
The answer, thankfully, is a simple, resounding, and incredibly exciting no. Not even close.
So what's missing? Well, for starters, remember gravity? It's not on the map. The standard model has nothing to say about it. The map also can't explain dark matter, the invisible stuff that seems to be holding our galaxies together, or dark energy, the mysterious force that's making the universe expand faster and faster. Oh, and it can't tell us why the universe is made of matter at all, instead of its opposite, antimatter. So, yeah, these aren't small details. They're some of the biggest puzzles in all of science.
So what could be hiding in those blank spots on our map? Well, physicists have some ideas. They predict a particle called the graviton, a kind of ghost particle that would carry the force of gravity. If we found that, it would change everything.
There's also this really beautiful idea called supersymmetry. It suggests that every particle on our map has a secret, heavier twin, a super partner. It would be like discovering a hidden, mirror version of our entire universe of particles.
And what about that dark matter problem? Well, a lot of scientists are on the hunt for a hypothetical particle called the axion. It's one of our best bets for what that invisible, galaxy-holding stuff might actually be.
The real point here is that this story is far from over. We've created this incredible, detailed map of reality, but we know for a fact that there are whole new continents of physics just waiting over the horizon. The modern-day explorers are out there right now, looking for them, and the only question left is, what amazing things are they going to find?